Objective: to describe stoichiometric defects in ionic crystalline solids. We have already learnt about the stoichiometric defects in non-ionic crystalline solids. Now let's understand the stoichiometric defects in ionic crystalline solids. Ionic solids always maintain electrical neutrality. So instead of simple vacancy or interstitial defects, ionic solids exhibit Frenkel and Schottky defects. In ionic compounds with Frenkel defect, some of the ions, usually smaller in size, get dislocated from their original site, thus creating a defect, as shown in the visual. This creates a vacancy defect at the original site and an interstitial defect at a new location. As Frenkel defect arises due to the dislocation of ions, it is also known as dislocation defect. Frenkel defect is found in ionic compounds that have low coordination numbers. Ions have large differences in their sizes. Since cations are smaller than anions, they can easily fit into the vacant spaces in the lattice. Cations are highly polarizing, while anions are easily polarizable. Consequences of Frenkel defect. Frenkel defect does not alter the number of cations and anions in the solids, hence the density of the substance remains unchanged. The closeness of like charges tends to increase the dielectric constant of the crystal. The crystal conducts electricity to a small extent by ionic mechanism. For example, in silver chloride crystal, an Ag+ ion occupies an interstitial site, leaving a vacancy at the original site. Zinc sulfide, silver bromide, and silver iodide are other examples of crystals with Frenkel defects. When cations and anions are both missing from their regular sites, the defect is called a Schottky defect. Here are some of the consequences of Schottky defects. In a crystal with a Schottky defect, the number of missing cations happens to be equal to that of the missing anions. Thus, the crystal remains electrically neutral. But the crystal begins to conduct electricity to a small extent by ionic mechanism. As the number of ions decreases as a result of this defect, the mass of the solid decreases while its volume remains the same. Hence, the density of the solid decreases. The presence of too many voids lowers lattice energy and thereby the stability of the crystal. This defect is commonly observed in ionic solids that have cations and anions of almost similar size. This type of defect is exhibited by highly ionic compounds that have high coordination number and small difference in the sizes of cations and anions. Sodium chloride, potassium chloride, and cesium chloride are well-known examples of crystals with this defect. The number of Schottky defects in ionic solids is quite significant. For example, a crystal of sodium chloride is observed to have about 1 million Schottky pairs per cubic centimeter. Silver bromide shows both types of defects, that is, Schottky and Frenkel defects. Let's summarize. In ionic compounds with Frenkel defect, some of the ions, usually smaller in size, get dislocated from their original site, thus creating a defect. When cations and anions are both missing from their regular sites, the defect is called a Schottky defect. Frenkel defect does not alter the number of cations and anions in the solids, hence the density of the substance remains unchanged. In a crystal with Schottky defect, the number of missing cations happens to be equal to that of the missing anions.